Logistic regression is a linear model of classification. That is why we firstly need to remember what's the idea of linear classifiers. If we have two classes, this is a problem of binary classification, and the idea is that there exists a hyperplane which separates classes from each other. We know that every hyperplane in space X can be defined using this equation. Scalar product of Wx is equal to 0, where the vector W is a normal vector for the hyperplane, and it is also the vector of the parameters for the classifier. On different sides of the hyperplane, there are different signs of the scalar product. For blue dots, it is sign plus, and for red dots, the sign is minus. That is why we can define a classifier A as a sign of the scalar product W and X. Also, we need to remember the notion of margin. For every object I, the margin Mi is defined as a product of the label of the class and the scalar product of W and Xi. So suppose that we deal with the positive class with blue dots. As the class is positive here, then Yi is positive, and if our classifier predicts correctly, then the sign of this scalar product will be also plus. When we multiply two positive numbers, we get a positive value for the margin. But if our classifier predicts incorrectly, the sign for the scalar product will be minus, and the product will be negative. If we deal with red dots, the situation is similar. The label of the class is -1, so Yi is -1. If we correctly predict the class, we get negative scalar product. When we multiply two negative numbers, we get a positive number. While if our classifier predicts incorrectly, the scalar product here will be positive and we will get negative Mi. So summarizing this all, we can conclude that Mi is positive if the classifier A predicts correctly, and Mi is negative if A predicts incorrectly. As our aim is to minimize the error of our classifier, this means that we need to minimize the proportion of incorrect predictions. We construct the loss function as the proportion of incorrect predictions when our classifiers fails to predict the correct class. This expression can be also rewritten in terms of the margins as a weighted sum of indicator functions for margins to be negative. This indicator function is discontinuous. Thus, we can't apply most of the optimization methods to minimize Q. In particular, we can't use the most favorite method for optimization, the gradient descent method. and the non-smooth minimization methods are difficult to implement. The solution to this problem is to use a smooth evaluation to this function, which we denote as L. The function L of mi should bound the indicator function from above. If we found such a function, then we can estimate the loss function Q as a weighted sum of these smooth functions L calculated in mi. On this slide, we consider several examples of estimating functions for the indicator function. First of all, study the behavior of the indicator function. On this graph, we see that the indicator function has a discontinuity at the point 0. The first variant of estimating function is a piecewise linear function, which is here drawn in orange. We see that at each point this function is greater or equal to the indicator function. The situation is similar to the next example, the exponential function, which is here drawn in blue. And the last example, logarithmic function, is here drawn in green. And I want to attract your attention to this function because we will use it today in our further studies. Of course, the set of possible estimating functions is not limited to these 3 examples. Moreover, this set is infinite. But using different estimating functions, we obtain different models of classification. It is important then to understand how can we interpret the performance of a classifier at each case, and which of the estimating functions should be used in a particular situation. Now we consider one of the possible principles of classification, which underlies the method of logistic regression. In this picture, we see a binary classification problem. We have 2 classes, class of red and class of green. This blue line is separating hyperplane, which for 2-dimensional case is just a straight line. It's reasonable to think that we can be more confident in the results of classification for the objects which are far from the hyperplane. So the following objects for red class and the following objects of green class. While the classification results for the points which are close to the hyperplane can be doubtful. We can measure our confidence in terms of distance to the hyperplane, or in other words, in terms of margins. Suppose we have 2 new objects S and T, which belong to red class. The object T is classified correctly and its margin is positive and large in absolute values because this object is far from the hyperplane. Object S was classified incorrectly, that is why its margin is negative and it is small in absolute values. It's natural to determine our degree of confidence using probability. We can assume that the classifier somehow calculates the probability of being red using the distance to the hyperplane. For the object T, our classifier considered that this probability is large, and for object S, small. So we decided to classify objects using probability. Denote P of x, a conditional probability for the object x, to be in the positive class. Then 1 minus P of x will be a conditional probability of belonging to the negative class. Since we should associate the probability of belonging to a positive class with a hyperplane, we should associate P of x with the dot product of w and x. Maybe we can model P of x by w dot x? Unfortunately not, because P of x as a probability lies within the interval 0, 1, while wx can be any real number. So we should somehow transform P of x. Let's try to use such transformation. P of x over 1 minus P of x. Maybe we can model this fraction by w dot x. Again not, because this fraction lies in the interval 0, infinity. We should widen this interval. And the simplest way to widen is to use the logarithmic transformation. Maybe we can model a logarithm of this fraction by w dot x. Yes, because this expression lies in the interval minus infinity, infinity. By the way, let us write some definitions. This fraction P of x over 1 minus P of x is called odds, and the logarithm of this fraction is called logit. Logit is often used in different estimating algorithms. We've got an equality, logarithm of P of x over 1 minus P of x equal to w dot x. And now we should yield P of x from this equation. Firstly, we exponentiate both sides of the equality, and then we can yield P of x from this expression. We've got that P of x is equal to such a fraction with exponent in the numerator and in the denominator. We can divide both parts by this exponent and rewrite it in terms of sigma function. In mathematics, sigma function is defined as a fraction 1 over 1 plus exponent of minus z. We've got a probability for the positive class, and a probability for the negative class will be sigma of minus w dot x. Now we've got the expressions for probabilities, and we should write the rule for our classifier. So the classifier will classify an object as a positive class if sigma of w and x will be larger than some cutoff, and it will be a negative class if sigma of w dot x will be less or equal the cutoff. Usually the cutoff is taken to 0.5, but other values can be also used depending on the task. We unite expressions for P of x and 1 minus P of x in one expression. We set probability of belonging to the ith class equal to sigma of the margin of an object. Finally, we go to the problem of estimating the parameters of the classifier. The idea is that we need to find estimates wj such that for positive objects, the probability of belonging to the positive class tends to 1. And for negative objects, the probability of belonging to the positive class tends to 0. In the regression model, we used least squares approach to estimate the unknown linear regression parameters. Although we could use least square approach here, which will be nonlinear least squares, the more general method of maximal likelihood is more preferable as it has better statistical properties. To put it simply, we seek estimates for W's such that the predicted probabilities P of x for each object corresponds as slowly as possible to the observed statuses. We defined likelihood function of V as joint probability of observed statuses. And here we assume that all objects are independently distributed. In this case, we can rewrite this joint probability as a product of marginal probability of belonging to the ith class. To fit the model, we should maximize this function. Now we transform our likelihood function and get another optimization problem which is equivalent to the initial problem. In practice, it is more convenient to maximize the logarithm of the likelihood function. It is possible because the logarithm is monotonically increasing function of its arguments, so the maximization of the logarithm of a function is equivalent to maximization of the function itself. That is why we can write here logarithm of the likelihood function in the left side of our equation, and we should add logarithm to the right side of our equation. So here we get another equivalent optimization problem. We should maximize log likelihood. Why is it important to transform our likelihood function? Because we can face a problem here if we try to maximize this product. The product of large number of small probabilities, because probabilities here are numbers between 0 and 1. So a large number of small probabilities can easily underflow the numerical precision of the computer. That is why we will resolve this problem by computing instead the sum of logarithm probabilities, because we know that there is such a property of logarithm that logarithm of a product is a sum of two logarithms. So now we will use this property and rewrite this part of our equation. So logarithm of this product can be rewritten as a sum of logarithms of these probabilities. Probabilities of our class to be yi on the condition that we have those x's and y. Now we rewrite this expression, replacing the sigma function with its formula. First of all, we should write it using sigma function, and then we will replace it. So as we mentioned before, our probability can be computed as a sigma function of margins. And now we will replace this sigma function by its formula, and we get sum of logarithms of such a fraction. So here we have exponenta in the denominator. Let's remember one more property of logarithm. When we take a logarithm of a fraction, it can be rewritten as a logarithm of the numerator minus logarithm of the denominator. Logarithm of 1 is equal to 0. That is why here we get minus logarithm of denominator. Okay. Now we can take out the minus from the sign of our sum. So it will be minus sum of logarithms one plus exponenta okay, and this expression should be maximized. By W. We can rewrite it in another equivalent form because maximization of such an expression is the same as minimization of the expression without minus. And we get an equivalent optimization problem of minimization. Also, let me remind you that the natural logarithm can be expressed in terms of the logarithm base 2. Logarithm of z is the same as logarithm base 2 of z over logarithm base 2 of e. As our denominator here is constant, we will write it that it is constant. We obtain new equivalent optimization problem where we minimize the sum of logarithms base 2. We got a new formulation for the considered optimization problem. Here on the left side of this expression, we see a familiar function. This is the estimator of loss function when we use the logarithmic function to estimate the indicator function. So we can conclude that building a logistic regression using the likelihood approach is equivalent to minimizing the loss function when using the logarithmic estimator for the indicator function.